different. It's actually true that it's not true there's a smooth transition. So as you get close to the speed of light, the laws start changing and changing, and as you get really close to the speed of light, they change more, but there's a smooth transition. As long as you're less than like a quarter the speed of light, you can forget about relativistic effects, depending on how precise you need to be. So yes, and is it possible that gravity works on a different scale? Yes, and I will address that later. How could it be we got the mass prediction wrong, i.e. more from black holes and brown stars than we predict? That is ruled out now, but it wasn't ruled out originally, and that's a good idea. That's a good thought, and that was certainly a possibility, and I will talk about that a little bit later too. What would I expect if galaxies were uniformly distributed through all space? In that case, the gravity of dark matter would cancel out on galaxy scales. It wouldn't affect the rotation curves of galaxies at all. It would affect the expansion of the universe, but if it was uniformly distributed through all space, it would not affect the motion of galaxies at all, because there's the same amount of dark matter in one direction as another, and that would offset. So it would only be seen on the expansion of the universe. Right? Here's another thing. We've looked at our galaxy, we've looked at other galaxies. In fact, here's a plot of a whole bunch of galaxies, and you can see that they all kind of follow this curve of a rising curve and then kind of flattening out. It's not all perfect, but they're not all perfect, but they all have the same basic shape of rising and then flattening out. So you look at spiral galaxies, and they all do kind of the same thing. Could dark matter be black holes and dark energy be Hawking? Dark energy is not Hawking radiation. Dark matter be black holes. I'll talk about that later. The sun is not at the center of our galaxy. In fact, let me go back a couple of slides here. I'll show you where our sun is. Previous. Our sun's about here, actually. Our sun is the circled star. So if you look at the disk of our galaxy, our sun is something like halfway out. So our sun is not at the center of our galaxy, but it's off-centered. So yes, dark matter occurs in the outer regions of galaxies, but actually it occurs all the way through galaxies. It's just it's spread out farther than the stars. So that's why halos are mostly dark matter. Towards the center, it's a better mix. Now here's another thing. I talked about velocity dispersion. What happens when you have a messed up? And this is when you look at an elliptical galaxy, or a galaxy that's a big mess of colliding galaxies, which actually is sort of what an elliptical galaxy is, or if you look at clusters of galaxies. So in a cluster of galaxies, you have both elliptical galaxies, which I've represented with little red blobs, and spiral galaxies, which I've represented with these little spirally thingies. And they're all flying around every which way. Some galaxies are going slower than others, some are faster, and it's a big, huge mess. However, you can look at sort of the average speeds or the distribution of speeds. And so if you first of all, the average speed is going to be 0, about the center of the cluster. But the velocity dispersion is what we call sort of the average offset from 0 if you take just the speed of the galaxies, right? So the velocity is 0, because some things are going one direction and some things are going another direction, and velocity is speed plus direction. But the average speed is not 0. So we take the average speed, that's something like what we call the velocity dispersion, and it's dispersion because its velocity is going every which way. If you look at the velocity dispersion in a galaxy cluster, and you compare that to the mass of all the galaxies you expect from looking at the amount of stars that you can see in the galaxy, the velocity dispersion is much too high. And this was noticed back in 1933. Fritz Zwicky, a well-known astronomer who was also an astronomer who had some trouble getting along with other astronomers. Nobody wanted to believe him because he was a strong personality. So people didn't really want to believe him because he was annoying, but he was right. He's had this inspiration early on. Look at these clusters of galaxies. Look how fast they're moving. They all ought to be flying off into intergalactic space, and yet we see lots of galaxies, clusters of galaxies out there. So something's got to be holding them together. 10 to 100 times the mass is missing. All right? Zwicky noticed that. Later on, when Sandy Faber started talking about spiral galaxy curves, Sandy Faber was one who I think was a little more politic than Zwicky, and so people believed her. But of course, now we look back and we realize everybody was right. That most of the mass in galaxies and galaxy clusters we're not seeing. When we add up all the stars and gas that we can see, we're not accounting for most of that mass. Here's another line of reasoning. All right, so the kinematics were the first line of reasoning. This and the spiral galaxy are the first line of reasoning. In many ways, they give us the best precise measurements of the amount of galaxies. And these are all Doppler derived as well. So basically what you do is you look at the overall average Doppler shift of each galaxy in the cluster, and then you can figure out how fast the galaxy as a whole is going. Right? So kinematics are strong evidence for dark matter all by themselves. There is other evidence. Cosmology, for example, which I think I clicked next, so I hope it shows up. Next. There we go. Okay, there's a whole lot of information on this slide. One is plotted. First of all, we use these special letters because, I don't know, we like to have our own special language to make everyone else look confusing. Omega M is mass density, and when we say mass, we mean regular matter plus dark matter. So that's what's plotted along this horizontal axis, and they're plotted in units that are normalized, and don't worry about what they are. They're just some freaky unit where the omega M is probably between 0 and 1. So that's the mass density of the universe compared to something we call the critical density. And then omega lambda is the dark energy density, so that's what's plotted along this. And then we've got 3 different experiments that are plotted. So first, BAO, baryon acoustic oscillations. Well, that's very technical, but basically it's telling you about clustering of galaxies. If you look how well galaxies cluster to each other, it says that somewhere, I'm going to make my laser red so you can see this, somewhere in these green lines is where we expect these 2 parameters to fall. So you see it's not very sensitive to the dark energy density, because the dark energy density could be anywhere along here. But it's very sensitive to the mass density. It tells us the mass density has got to be somewhere between like 0.25 and 0.5. All right. That's what BAO tells you. That's what clustering of galaxies. CMB is observations of the cosmic microwave background. Cosmic microwave background is sensitive to the sum, mostly. And the cosmic microwave background tells us that the sum of omega lambda and omega M has to be close to 1. All right. And then finally we have supernova observations, and the supernova observations are the best sort of direct evidence that the expansion of the universe is accelerating, the best direct evidence for a cosmological constant, and they're most sensitive to something like, and I did it wrong, this should have been omega M minus omega lambda. That little thing right there is supposed to be a minus. So the supernova tells us the parameters have to be somewhere in here. And you notice all 3 of these collide in this one spot. And this one spot is around omega M of 0.3 and omega lambda of 0.7, something like that. Okay? Well, here's the neat thing. If I take out all the galaxy clustering, which means I can throw out all the stuff about kinematics I told you before, and we're looking at 2 completely different things. Look at the cosmic microwave background, which I talked about a month ago. And look at the supernova results. And you put the 2 together tell you, well, they only overlap here. And the 2 together give us the same thing that the galaxy clustering results give us by itself, that omega M has to be about 0.3. All right. So, and again, I'm not going to talk a lot about the expansion going faster and faster. It's probably not going to stop. It's probably not going to go backwards, but that's a whole other talk. So I'm going to defer that either to the end or to the next Wednesday Ask an Astronomer. The point here, though, is that if you look at just the stuff I talked about before, but if you look at these other cosmological observations, it tells you to explain our cosmological observations, we need this much mass in the universe. The total mass in stars and gas we see is somewhere around 0.0 a few. I don't remember if it's 0.01 or 0.03 or 0.04, but it's 0.0 a little bit. That's all the mass in stars and gas. We need to have something like 0.3. So there's a factor of 10 missing in mass. So there's got to be dark matter. There's more mass than we can see. Here's another cosmology argument. Structure formation. Start from the cosmic microwave background. That's the mass distribution a few 100,000 years after the Big Bang. Do calculations of how structure grows. So where there is, let me move it away. I'm getting all excited and talking loud. So where there's higher density, stuff is going to kind of collapse, and you're going to make clusters of galaxies. And where there's lower density, well, stuff's going to collapse away from that. You're going to make voids. And if you do those calculations, you can get a distribution that looks something like this. So this is from a calculation. Over here is real data. This is from the Sloan Digital Sky Survey. All right. So notice what you see. Well, you see these clumps, sort of like there, and you see these voids between them. And here's a simulation of that data that shows you basically the same thing. But now now you won't see exactly the same pattern, because this is a simulation that doesn't have exactly the same, it doesn't show all the galaxies in exactly the same place. But the basic way it looks is the same as here. Right. To get this simulation right, you have to put in dark matter. You have to put in more matter than we can account for just looking at all the stars and galaxies. So For the cosmology to work, we need to have this dark matter, right? So 2 lines of evidence I've given you now. One is the kinematics that says there is more matter holding together galaxies and holding together clusters of galaxies than we can see. The second is cosmology. In order to explain the observations we see of the universe as a whole, be it the expansion of the universe and the cosmic microwave background put together, or being it large-scale structure, clusters of galaxies and superclusters and the voids and the filaments. In order to explain all that, we need dark matter. We need to have 30% of the energy density of the universe in dark matter, and yet the amount of mass that we see only corresponds to about a few percent. So what does all this mean? There's more mass in galaxy and in clusters of galaxies than we can account for from the stuff we can see. Dark matter, the stuff we can't see. But what is it? What is dark matter? And this is where somebody asked a good question earlier. Dark matter candidates, one-time dark matter candidates, and I say one time because we've kind of ruled out the first one. So we start with MACHOs, massive compact halo objects. It's a, if you're going to have to name everything after an acronym, you might as well come up with some fun acronyms sometimes. So MACHOs. MACHOs, what are they? Massive compact halo objects means things out in the halo of our galaxy. Possibilities include very dim, undetected stars. It was possible that red and white dwarf stars both are small enough and dim enough that we can't see them very easily very far away, and maybe we just haven't accounted for all the red and white dwarf stars there are. Very real possibility, okay? It may be that there were just lots of red and white dwarf stars out in the halo that we had not detected yet, and that's all the dark matter was. It was not dark matter, it was just insufficiently bright matter as such, right? They could be what failed stars, which is applying all kinds of value judgments to brown dwarfs. A brown dwarf is a star that is not massive enough to support fusion at its core. In that sense, it's a failed star because it never really became a star, right? So, yeah, and so Bowers, could you tell if it's diffuse or dense? Yes, they could. And in a sense, if you have lots of stars spread out, that effectively is diffuse mass. But if they're compact halo objects, there will be specific things. I'll mention that in just a second. All right, gas we haven't detected, or black holes. Actually, gas we haven't detected would not be MACHOs, so I shouldn't have listed that here. Or black holes. Okay, so these other things are all MACHO candidates. Well, people have done searches for MACHOs, and what they do is they look at a very dense star field, and as a MACHO moves in front of a background star, it will briefly gravitationally lens it. So there have been MACHO searches that do exactly this. And they found some, right, that you find dim stars out there, or maybe brown dwarfs, but they have not found nearly enough to account for all the dark matter. So there's not enough MACHOs to be dark matter. The other leading dark matter candidate is, of course, WIMPs. If you have MACHOs, you have to have WIMPs. WIMPs for weakly interacting massive particles. These are all diffuse. WIMPs are defined by they do not interact electromagnetically, including with light, which is electromagnetic. They do interact via gravity. They may interact via the weak force. So the weak force is one of the 4 forces of nature. It is the force that's responsible for a lot of radioactive decay. It's not the thing that holds atomic nuclei together. It's much weaker than that, and that's why it's called the weak force. Neutrinos are an example of something that fits all 3 of these. Neutrinos do interact via gravity. We know that neutrinos have some very small mass nowadays. They do not interact electromagnetically, but they do interact via the weak force. So WIMPs are something similar to neutrinos, but they're not normal matter. They're not made of protons and neutrons and electrons because protons, neutrons, and electrons interact electromagnetically. So WIMP. And all right, and so massive sounds big. When we say massive particles, what we mean is not massless. That's correct. But what's more, almost certainly they're more massive than all the particles that we've made in particle accelerators today. The reason being, how massive a particle is tells you how much energy that particle has. If it were low enough mass, we probably would have made them. Yes, neutrons do interact electromagnetically, it turns out. They don't have a charge, so they don't interact with electromagnetic or electrostatic force, but there's a magnetic moment on neutrons. So they will